Hello everyone, I'm Bingyu from the University of Notre Dame. Today I'm very happy to share with you our work, Automatic Virtual 3D City Generation for Synthetic Data Collection. As the convolutional neural networks achieved huge success in various computer vision tasks, lots of them now have practical usage in the autonomous driving field. These tasks include, but are not limited to, object detection of targets on the road, syntax detection in the wild, 3D object detection, and traffic sign detection and classification. Solutions to these tasks are usually complex neural networks consisting of hundreds of layers. As neural networks become deeper and deeper, their performance in the previously mentioned tasks also hits record high. However, deep neural networks are data-driven. To train a model with good performance, it usually requires a significant amount of images or videos. While real-world datasets are always the best to use, a common issue of real-world datasets is that they are extremely expensive to collect and annotate, and existing real-world datasets have various limitations. For example, COCO is a general dataset for object detection and segmentation, but it doesn't contain many road scenes. Kitty and traffic sign dataset LISA are road scenes specific, but are of small scale and variety when compared with COCO. Data augmentation, therefore, is a widely used technique to generate more training data for deep neural network models. However, existing data augmentation methods such as geometric transformations or generative adversarial networks are restricted from generating videos or images with diverse city scenes. Therefore, in this work, we proposed a pipeline to automatically generate virtual 3D cities for synthetic data collection related to city scenes. It's highly efficient and easy to use. The input is just an image sketch with color blocks. The pipeline then generates outputs of 3D city objects ready to render. The objects are assigned with high-quality textures, which can create highly restored city scenes. With the help of 3D render engines, we can simulate the city scenes under different daytime. Finally, the output 3D city models can be used to generate training data for multiple tasks depending on the needs. Let's take a look at the input to the pipeline, which is an image representing the layout design of the city model to be created. We consider three types of key components in the input image: buildings, roads, and street lamps. And we represent them using different color blocks so that it's not only easy to generate but also easy to detect. The pipeline can either generate layout images or take custom layout images following the constraints. Given a layout image, we firstly determine the coordinates of buildings. The blue area represents the blocks where buildings are to be placed. We firstly detect the coordinates of the block boundary and then place buildings inside following an algorithm we designed. The algorithm randomly places buildings in a block from left top to right bottom and left as little empty space as possible. Then, the starting and ending points of rows will be extracted and intersections coordinates will be calculated. For street lamps, we will place them along the side of rows with a fixed distance, and if two lamps are too close to each other, we'll arbitrarily remove one. To generate real-world-like city scenes, we assign buildings with facade textures from the CMP dataset. It consists of 600 rectified images of facades from various sources, and all the images have been manually annotated of building components, such as window, door, balcony, and etc. Facade images are cropped to contain only the parts below the first molding to prepare a building texture. We further annotated the images with floor number and rescale each facade to ensure a consistent floor height. This further enhances the visual quality of the output scene. To recap the pipeline, we firstly generate the input layout images with color blocks representing different city elements. The coordinates of buildings, roads, and street lamps are then extracted. Buildings are assigned with corresponding textures. Then the 3D city model will be constructed with elements in place. The object is now ready for render. Each step costs just seconds, and on average, the whole pipeline takes around 35 seconds to generate a city object. After the city has been constructed, we can make use of it by inserting elements according to our needs. For example, we can place text planes on the wall of buildings in the city to generate synthetic training data for syntax detection tasks. The render engine will create distortion and reflection effects just like in the real world. Or we can place road signs along the roads, and by changing the environment parameters, the render engine can simulate the extremely low illumination during night in the real world. Since the bounding box of object inserted can be returned by the render engine easily, in this way we can generate an unlimited amount of training data with little effort. In this work, we firstly proved the effectiveness of the synthetic training data generated by our pipeline for the syntax detection task. We trained an object detector of the faster RCNN model with the CNN layers replaced by ShuffleNet. We compared the performance of our generated synthetic images with the Synthetex dataset and ICDAR 15 training set. As quantitative results shown, using the images generated by our 3D city model achieved a comparable F-score and the best precision rate among the three datasets. This demonstrates that our method is capable of generating valid training data for text detection tasks. As shown in the sample images, the 3D environment is able to mimic the distortion and reflection of text instances in the real world. Therefore, the model can learn the characteristics of text under various conditions. We also collected a dataset for the traffic sign detection task. In these experiments, we proved the feasibility of using our output 3D city model to create scenes with different daytime settings and provide training data for traffic sign detection during night. We chose the same object detection model used in the syntax detection experiment and trained it for traffic sign detection. The detection performance is compared between the model trained with only the images under daytime setting and the model trained with images from daytime and further fine-tuned with images from the nighttime settings. As shown in the table, fine-tuning the object detection model with nighttime images achieved significant improvement on both precision and recall rate. After fine-tuning with nighttime images, the detector can retrieve traffic signs under extremely low illumination conditions. To conclude, in this work, firstly, we develop a pipeline that can take a 2D sketch as input and generate a 3D city model according to the information embedded. Secondly, the output virtual 3D city models are assigned with real-world facade textures and can be directly modified and rendered using 3D development tools. Finally, the syntax detection and traffic sign detection experiments in this paper proved the effectiveness of 3D city models generated using our pipeline as the training data source. Thank you for listening.